I got 2 turntables and a microphone. Record that, baby. Okay, here we go. So we were checking for normality on the DVs, which means all the F and the FB, all those guys. We're going to go to Analyze, Descriptives, Explore. We're going to kick them all in at the same time. Scroll down, hit the Shift key. We're going to go through Dora, the Explorer. We're going to go to Plots. Stub and leaf we don't use anymore. Histograms can be misleading, but we're going to check them anyway. This is your money box normality. This will run a mathematical test to tell us if the data is normal or not. Normality is one of the assumptions of a t-test. The data has to fit a normal distribution curve. Doesn't have to, but there's tricks. And it's going to take a second because it has to do them all. Okay, here they all are. So you got 208 of each one. You do have some missing, but 208 is plenty. So here's the means and standard deviations of everybody, which is interesting, but we don't really need it right now. This is your test. So there's actually 2 tests of normality here. The Kolmogorov-Smirnov test, the Russian guy, and the Shapiro-Wilk test, the Jewish guy. So how you tell if a data set is normal or not is if the sig value is less than 0.05, that means it violated normality. So F violated, FB violated. In fact, they all violated.
All violated.
Except for a couple of them. Now that 200.200 star, that's the software saying, you know what, if you had a bigger sample size, it probably would be normal. But then you switch over to the Shapiro. Most of these are also, they're agreeing with that. So in other words, the data set is not normal, which is strike one, which means we probably should not use a t-test. Okay? But we're going to run one anyway. So now we're going to run the t-tests, and we're going to do analyze, compare the means, independent sample t-test, and we're going to do 2 and 4. So it's for the male violence versus the female violence. And this is going to be for D. Right? Is there an option for a one tail? No, I don't think so. I don't think so. Bootstrap, we never use bootstrap. That's for the bad guys. And again, there is no significant difference. So we're going to divide this 2-tailed by 2. So yours is going to be about 37.37, which is still way above 0.05, so there's no significant difference. And again, I'll fix this when I transfer it to a Microsoft Word document. Now, part 2, we're going to go to Analyze, Compare Means, Independent Samples. This time we're going to do the 1 versus 3, which is female nonviolent to male nonviolent, yes?
Correct. And we can do all 3 of the scales in this one. So P, A, S, C, and M, A.
So Pa, Ma,
and Sk.
And Sk. And the Skyon. Okay, there we go. Boom. So again, we're going to divide these by 2 because it's a one-tail test. So Pa becomes borderline. In fact, if you had a bigger sample size, it probably would be significant. And in SC, same thing. So you got 2 borderline significance. Next.
2 and 3 by PT.
2 and 3. So that's male violent. No, female violent versus male nonviolent.
Correct.
Got it. And what's the test variable? What's the DV?
PT.
PD is in police department?
T as in Tom.
T is in Tom.
Tom, down.
PT is in Tom. There you go. Ready? Boom. Nope. Even if you divide the sig value by 2, you're still talking about 1 0.12, which is well over 0.05. So no significant difference there. Next.
That's it.
Okay, so no. Then we wanted to run basically, and I don't know if this is a good idea or not, maybe you can tell us, but what was suggested was that we run all of like the female nonviolent by each of the other ones to see, and I don't know what test this would be either, to see if there's any differences between any of the 4 groups by each counterpart. So basically we're looking at female nonviolent between female nonviolent and female violent, female nonviolent and male violent, female nonviolent and male nonviolent, and then seeing if there's any differences between anywhere on the groups.
That's what we would call an ANOVA.
Okay. And
Now,
are we able to do that with unnormal data?
Yeah, it's the same thing, you know. Now, once we're done with this, I'm going to switch over to the non-parametric version, and we should expect the same results. Usually you do, not always, you know, but 99% of the time you do. So what we're going to do here is we're going to do a multivariate analysis so we can check them all at the same time. Again, this is we'll check and see if there is one in the long list, then we'll repeat it singly. I don't want to overly confuse you guys, but watch. We're going to go to Analyze, General Linear Model, Multivariate, and we're going to stick all of these in at the same time.
Okay.
It just makes it a lot easier, so I don't have to run 15 different ones. And then we're going to stick it in by group. So this is going to look at the 4 different groups.
Okay.
And if one of the values is significantly higher or lower, then you should get a significant difference.
Okay.
So that's what we're going to do first, and it's just a real quickie.
If we're does it matter if we're predicting directionality in any of them, or like this is strictly exploratory because we don't really have predictions for these? So the 2-weighted or 1-weighted, what would it be?
These are all one-way tests. In fact, right, so the t-test is the grandfather of all statistics. That's the only one where you have to worry if it's a 1-tail or a 2-tail.
Gotcha.
But everything past that is simply a 1-tail. They chopped off that 2nd tail. So here we go. No. Don't care about that. Don't care. Here's your bunny box right here. So F, that's your DV. And it says there is a significant difference in there somewhere. In fact, look at all these things. There's a significant difference in there somewhere.
And that's saying that there is a significant difference on one of the scales?
On all of your scales. So that's what this means.
Okay.
So let's double check. Yeah, okay, so we're going to go back up to the means box. And here they are right here.
Gotcha. Okay.
So let's look at the means. The trick is to find the lowest and the highest. The lowest is 50. The highest is 73. Significant difference for sure. Right? That's 23-point difference.
On F, we have 50, or I guess we'd go FV or FNV and MVO.
Correct. So from the female nonviolent to the male violent, huge difference in the F scores. In fact, your male violent, I'm looking at them right now, they're violent. Or whatever you're measuring, they're way high. So same with FB. The low are the female nonviolent, the high are the violent males. L, no. So this one's a little bit different. It's probably measuring something different. So you got a low of 49 and a high of 59. So that's a difference of 10. That's significant. In fact, they're all significant already. We know that already. And then here you got a female nonviolent 53. No, I'm sorry, male nonviolent 55. Male violent 45.
So for L, sorry, go back up. For L, the difference was between female violent and female nonviolent?
It was probably between female violent and all 3 of these other ones. No, between these 2 right here. Between female violent, female nonviolent. Now, if you guys want to pick a specific DV and just do one, we could do that, and then that would give us a little bit more information. Like we could run a Tukey test to see exactly between which groups are significant, which ones aren't.
I like that idea because this is difficult and hard to comprehend.
And okay, so you want me to do it just for L? Or you want me to do it for all of them?
Can we do each for all of them?
Yeah. Okay. Let's see what that looks like. Okay. Here we go. Analyze regression. Let's see. I think I can do it as a multivariate. Yep. We're going to use the Tukey test because I like saying the word Tukey.
All right. You like writing the word Tukey.
Tukey. All right. So this is the same results we already know.
Mm-hmm.
And so here's the bad news. Is the data violated the assumption of normality before. Now here's the Levine's test, which checks the second assumption, which means that the variance, remember the variance is the spread of the data, in each little group should be relatively the same, and this says it's not. So the spread of the data, the variance in the different groups is not the same for F, for FB, it is for L, it is for K, it is for S, it is not for HS, it is not for HY, it is for PD, it is, so about half and half it looks like here. So half of the data looks like it violated the assumption of homogeneity variance, the other half did not. But let's keep moving on, and we already know that there's a significant difference somewhere between the groups in all of these guys. So now we're going down to the Tukey test. Tukey, here we go. So there's F.
All right. That is so much more helpful.
So this is how you read it. So here's FNB versus FNBO. There's the difference, and it's significant.
Yes, I love this. This is great. Great. I understand this.
Good. FNB versus MNB, not significant. FNB versus MBO, significant. See that? That's how you read them. So let's find one that's got something here. So like for FB, they're significant between everybody except for FNB and MNB. That's the one that's not significant.
Okay.
Same thing. MNB, nonviolent men. Yeah, they don't seem to be significant anywhere. Those nonviolent men. But okay, right, this breaks it down into exactly between which two groups. Now, so this first column is the difference between the groups. So if you're going to quote the means and the standard deviations, you need to go back up to the means and standard deviations box on everything right here. It's right here. Right, this one got all the means and standard deviations for everything. Broken down by group. Now, so this is the ANOVA, right? Mm-hmm. So you're comparing 4 groups. The other ones we ran was a t-test. You're only comparing 2 groups. So two of your things were borderline. But once you start comparing all 4 groups, you got significance everywhere. So keep that in mind. And all right, we don't need to know that. It didn't violate. Okay, yeah, we don't need to know that. So, all right, what else you got?
Honestly, I think that's it.
Now we're gonna run the real test we're supposed to. So if a data set with a t-test, you can kind of get away with violating a little bit of the assumptions, right? But unfortunately, most of your data, right, your variables, violated both normality and the assumption of homogeneity. There's no way you could run a t-test.
Okay.
You would be kicked out of the statistics school. But we could run the non-parametric version. But again, the same thing. They should pretty much agree with whatever the t-test said. It's been my experience. It really doesn't matter which way you go. if there's a significant difference, it shows up on both tests. And if it's not, it shows up on both tests.
Okay, so then would we do the Man-Whitney U on this one?
That's the one.
Sweet.
Ashley, I'm so proud of you. So we're going to go to non-parametric. 2 independent samples. And we're doing, first one was 2 and 4, right?
Yes.
And it was D as in David.
Correct.
And the t-test said it wasn't significant, right?
Correct.
So don't expect significance here. So this is how you look it up. There's your Man-Whitney U test. And it uses mean ranks. Don't ask me to explain it because I don't think I can. But this is how you tell. You look at the z-score and then the sig value compared to it.
And that again is two-tailed, so we should do one-tailed. So cut it in half.
Correct. You would divide that by 2. So the p-value is 0.13, which still basically says it's not significant. So it agreed with the t-test. All right. Next one. Analyze. Non-parametric. So 2 of these should be borderline, as I recall.
Mm-hmm.
And this is 1 and 3.
Correct.
Now, you guys know everybody in your class, right?
Yes.
I'm wondering if he gave you guys the exact same shit. I mean, that's going to turn out to be bad. You guys might have to beat somebody up or something. So this was Ma, Pa, and SC, right? Ma, Pa.
Yes.
Right. So as I recall, Pa and SC were close.
Mm-hmm.
Right? Boom. So again, if we divide these by 2, only Pa is close. Right? Significant difference between the Pa scores.
0.053-ish?
Yeah, so it would be like 0.053, yeah. So it just barely missed it. So that's the one you call borderline.
SC was not after running this one?
No, nowhere close. Now, was there another one? I'll jump into the ANOVA ones now if you want.
Did you want to run the Man-Whitney U for the last one?
Yeah, what's the last one?
2 and 3 by PT.
That's the one. 2 and 3 by PP. 2 and 3. And you guys out. PT. And z-score, divide that by 2.
7, 8,
0.08. So you might be able to get away with calling it borderline. Some teachers say anything less than 0.1 could be considered borderline. I mean, yeah.
Okay.
All right, now we're going to do all the ANOVAs again, but this time we're going to use, I think it's a Wilcoxon test, but we'll just let the software do it for us, non-parametric tests. And we're going to go down to K independent samples, and we're going to stick in all of these bad boys. And there should be significance all over the place. Should be. And low group is 1, high group is 4. You can use everybody in between. Yes, you are. Right, this is a Kruskal-Wallis test.
K-R-U-S-K Wallis.
And here's your sig values right here on the bottom row. Everybody's significant, right? So this is kind of agreed with your t-tests. So you got significant differences everywhere in all tests between the 4 groups.
Okay. And then do you have to rerun Tukey on the non-parametric or no?
I don't think you can do that on a. Just use the Tukey from the t-test.
Gotcha.
Right. Now, what I suggest is you kind of do a fusion between the t-test and the non-parametric because they basically agreed with each other.
Yeah.
So then you can flip-flop back and you can say, you know what, there was a significant difference here, and then cite the mean and standard deviation from the t-test data. That it's so much, you get so much more data from a t-test than you do from these other things. That kind of thing. And then go down to the Tukey test and just say there was according to the Tukey test, there was a significant difference here, blah, 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 blah.
Okay. I understand. Do you understand?
I'm there. I'm following. I get it. I can see how to read it.
So again, the short version is, hold on a second.
Borderline.
Now you could go either way because again, this must be like the 35th time I've done this same test with the same data. Is that a kitty?
Yep. He's in a lovely little slider.
Oh my God, he looks like he's into Spider-Man. Oh, you poor kitty. You poor kitty. Run, kitty, run. Looks like one of my cats. Simon says he's a big old fat orange kitty.
No, they're the best.
They are the best. We have a yard full of cats. We have a lot of feral cats here. I've been here 8 years. And up until this COVID thing, I would capture them, take them down, get them fixed, and bring them back. If they didn't get picked up, if they didn't get adopted, which most of them did, I would bring them back and they live at our house. And we've got 5 cats that weren't adopted, but they've been with us for years and years and years. But now they stopped it last year, and we're up to our eyeballs in cats. And the teenagers are pregnant again. So
Oh wow! Oh
it's
great!
just, oh my God. Anybody want any cats? So hopefully they'll okay it again. So they gotta get spayed. When they get spayed, it's not a problem. They get fine homes, and if nobody will, we'll take them, and they love it here. I mean, it's like cat Disneyland around here. So
Ashley adopted one, a feral cat.
I did. I started feeding it. It kept coming to our door, and then my cat started like loving the cat and inviting it over more. And I was like, "Stop, bro."
that's how you tell.
We named him Vader.
That's a good cat name, Vader. Ooh, I am your daddy. So yeah, if your house cat likes them,
He sounds like that.
that's scary. Does he have a lightsaber? All right. Okay, what was I doing?
That was it. I think you answered all of our questions. And we're gonna attempt to write it up now.
Okay, let me stop the video, and I'll send it to you when I'm done with it.